It's a great pleasure today to have Junsei Tokuda telling us about Swampland conditions on scalar potentials from positivity bounds. Please.
Okay, so thank you very much for introduction. So I'm Junsei Tokuda from Kobe University in Japan, and I'm now first postdoc. And today I will talk about, today's talk is mainly based on this paper, and the co-author is Toshifumi Naomi. But also, today's talk also based on these works listed here in collaboration with Katsuki Aoki, postdoc in Kyoto, and Shinichi Hirano, postdoc in Nagoya University, and Planck in Cambridge. He's a student. Okay, so I will talk about the non-trivial relations between the UV completion of gravity and the low energy effective field theories. And these questions if such relations are clarified, then we can test some properties of UV completion of gravity. So such considerations can be very interesting. And indeed, such relations have been already investigated, and various conjectural bounds have been proposed, and they are so-called Swampland conjectures. And for example, if we consider the scalar EFTs, then of this form, then the bounds on the scalar potential V of phi have been conjectured. So for example, the strong scalar weak gravity conjecture or the Sitter Swampland conjecture and so on. But and if such bounds are true, then it's very interesting. But unfortunately, so far there's no rigorous proof. So under these situations, it is great if we have some clear way to derive such bounds. And in the context of exploring some new physics, as a unitarity has played an important role. And for example, the S-matrix unitarity has been useful for finding new physics, particularly in the context of non-gravitational theories. So for example, the W boson scattering, the perturbative unitarity of W boson scattering predicts the upper bound on the Higgs mass. And if we consider if we require the perturbative unitarity on the Euler-Heisenberg Lagrangian of this form, then we can say that the new physics must enter below the mass scale of ME without the knowledge of QED. So the S-matrix unitarity is definitely powerful, but more recently it has been recognized that we can get more information on UV theory by using the S-matrix analyticity and so on, in addition to unitarity. So for example, so if we consider this Euler-Heisenberg Lagrangian, then we can, by using the analyticity and so on, we can also say that the sign C2, a coefficient sign of C2 must be positive. And if we consider the scalar EFT of this form, then we can say that C2 must be positive. And this kind of bound is called a positivity bounds. And these are developed in the context of non-gravitational theories. But in today's talk, I will argue that the positivity bounds can be actually useful to derive the Swampland conditions on 4D quantum field theory coupled to gravity. And in particular, we discussed the positivity bounds on 4D scalar KFT coupled to gravity of this form in this talk. And then it is found that the scalar potential cannot be arbitrarily flat in a certain sense, which I will explain later, but I will show you some example here. So for example, if we consider the lambda 5-4 theory, a massive lambda 5-4 theory, then the massless limit with fixing the coupling constant lambda is prohibited. So this limit is prohibited. So this means that the mass is bounded from below. So, but I will explain later more detail. So today, from now on, I will first explain the positivity bounds, and then I will discuss the application to this 4D scalar QFT coupled gravity. Okay. So first, I will explain the formulation. So the basic idea of the positivity bounds is that not every consistent looking EFT can arise as an effective description of UV completion, which has some standard properties such as unitarity, Lorentz invariance, analyticity, and locality. And for example, as I explained already, if we consider the scalar EFT of this form, then the positivity bounds tells that these properties impose the positivity of C2. And this means that if the negative C2 is confirmed, then its UV completion must be exotic. And this positivity bound is almost established in the context of non-gravitational theories. And more precisely, the positivity bounds is the constraints on the EFT 2-to-2 scattering amplitude. And so I will briefly explain the derivation of positivity bounds. Because I will later consider the scalar theory coupled to gravity. So here I focus on the 2-to-2 scattering of a massive scalar phi. And I write this amplitude as m. And the scattering amplitude is a function of Mandelstam variables S and T. And S is just the center of mass energy square and so on. And the practical definition, more practically, in positivity bounds, a practical definition of the standard properties of UV completion is formulated in the language of the scattering amplitudes, and such properties are listed here. The first property is analyticity in the complex S-plane, which states that the amplitude must be analytic except the known poles and usual branch cuts, and this is implied by causality. And the second property is the high energy behavior of the amplitude, which states that the growth rate of the amplitude must be slower than the square in any direction in this complex plane, and which is implied by the Froissart bounds. And the third property is the positivity of the imaginary part of the amplitude in the forward limit, which is implied by the optical theorem. And the fourth property is the crossing symmetry. And to investigate how these properties are reflected in low energy theory, let us consider the EFT expansion of the forward limit amplitude of this form. And then in particular, the coefficients of S square is given by some integral, this complex integral defined in this way. Now here's S star is some expansion reference point. I will later choose S star to be 2m square. And then we can rewrite this integral in the language, in the UV language, by deforming this contour in this way. Okay, so in this way, the first term is a contribution from the branch cuts, and the second term is a contribution from the infinitely large circle. And the first term is ensured to be positive, although it cannot be computed precisely without the knowledge of UV completion, because it includes the integral of amplitudes at very high energies. And the second term also unknown without the knowledge of UV completion, but we can say that this part vanishes thanks to the boundiness property of the amplitudes at infinity, which is implied by locality and unitarity. And then we can conclude that the C2 must be positive. And this is the positivity bounds. So let me summarize so far. So the positivity bound states that the coefficients of S square, that is SC2, must be positive thanks to the analyticity, unitarity, and so on. And this is the formula. And this C2 corresponds to the coefficient of higher derivative couplings in this example, scalar EFT example. And we can further improve this expression by separating the EFT piece and the high energy piece in this way. So here the C2 lambda is defined. C2 lambda is defined by C2 minus the integral of imaginary part from 4m squared to capital lambda square. So here lambda is defined as the cutoff scale of effective theory. And then by definition, the C2 lambda is calculable within EFT. And then the C2 lambda is equals to the integral of imaginary part from above the cutoff scale. And this is which cannot be computed within EFT, but we know that this piece is positive. And physically, this piece corresponds to the contribution from EFT loops, and the right-hand side corresponds to the contribution from heavy physics. And this is so-called improved positivity bounds. And this is a known things, but the main question is if it is possible to extend these arguments to the gravitational context. And if possible, then we can put quantum gravity constraints on gravitational EFTs. And in fact, it is already noticed that if it's applicable, then it is noticed that the weak gravity conjecture type argument can be derived. But there is some obvious obstruction. And the obvious obstruction is that the gravity spoiled the proof of the high energy S-square bound of the amplitudes. And because the masslessness of the gravity spoils the proof. But however, the S-square bound is satisfied in known examples. And so in this talk, in this work, we simply assume the S-square bound up to the m Planck to -2 up to this order. And under this assumption, we try to derive the positivity bounds on C2. And still, this is just an assumption, but let me just mention that there is some argument that the square bound may be proved by using the ADS-CFT type argument. But anyway, so in this work, I just assume this property. So let me discuss what happens once this assumption is accepted. So again, let us consider the 2 to the scattering of a massive scalar with gravity, and then consider the EFT expansion of this form. Then, so due to the presence of gravity, the coefficients of S square is given by this C2 plus the contribution from T-channel graviton exchange. And then repeating the same argument as before, we arrive at this expression. And here, this is I just recall the definition of C2 lambda and so on. And then the problem is that the second term on the right-hand side, we have a divergent term in the forward limit. But we know that the C2 lambda must be regular in the forward limit. So this means that the first term, the integral of imaginary part, must be divergent. So this means that the right-hand side becomes kind of infinity minus infinity, and whose sign is unclear. So here, let me emphasize that the subtlety is due to the spin-to nature of graviton. And this is this T-channel singularity appears due to the fact that the graviton is spin-2, so that the T-channel pole contribute to the S-square coefficients. Okay. So here the key point is that the finiteness of the regularity of the left-hand side will require that the imaginary part must grow as fast as the square in the forward limit, which leads to the divergence of this part. While the S-square bound of the amplitude requires that the growth rate of the imaginary part for negative t must be slower than the S-square. And this property will lead to the Rech behavior of this form. So we assume the Rech behavior of this form, which is indeed realized in string theory amplitudes. And the Rech behavior is parameterized in this form. So here the f is some function of t, and the ms is is a scale of regularization, which corresponds to the mass of the lightest higher spin states, which is responsible for the regularization. And this alpha prime is positive. And we impose this rate behavior for high energy. And here epsilon parameterized that the rate behavior is realized for sufficiently high energies. And then under this, once we admit the rate behavior, then we can compute the problematic infinity minus infinity contribution. So we can compute this piece. And the result is this. So the first term is just an integral of imaginary part, and this is ensured to be positive. And the sum of second term and third term corresponds to the infinity minus infinity piece. And this bit is teacher pole, but we know that this must be canceled. So this imposes conditions on the rate behavior. And then we have some finite residuals, F0, which is given by this form. And because the first term is positive, so this shows that the C2 lambda must be larger than F0, and F0 is given by this. And unfortunately, the F0, the first term here must be negative due to unitarity. So we can not say that F0 must be positive. So this means that the C2 lambda can be negative, and we identify the negative term here, and whose precise value is determined by the details of the rate behavior. And we find that the unitarity admits a violation of the strict positivity once gravity is included. And because the rate behavior is realized by some tower of higher spin states, so it would be plausible to assume that the behavior of the typical scaling behavior of the rate amplitudes. So that we assume that the scaling of the rate behavior is determined by the higher spin, mass of the higher spin states. So then we arrive at this order estimation of F0. So let me summarize so far. So we clarify that we can derive the positivity bounds with gravity under some clear assumptions, which includes a mild high energy behavior and the rate behavior with single scaling. And we can say that this is indeed satisfied in known amplitudes. And under this assumption, we can arrive at the gravitational positivity bounds of this form, which states that the C2 lambda, which is kind of S-square coefficient, can be negative, but the allowed amount of negativity is suppressed by Planck scale and the higher spin mass of the higher spin states. Okay, so next I will explain the application. And I consider the 4D scalar KFT coupled gravity of this form and the potential. And in this talk, I consider the potential, renormalizable potential of this form. So the mass term plus the cubic coupling plus quartic coupling. And then we compute the C2 lambda and discuss the implication of this inequality. And in this talk, for simplicity, I ignore the non-renormalizable terms such as del phi force, but it doesn't change the essence. Okay, so this is the reminder of the definition of C2 lambda. So C2 is a square coefficient, and the C2 lambda is defined by C2 minus the integral of imaginary part. And so we can obtain the C2 lambda simply by computing the scattering amplitude at low energies within EFT. Okay, and this is just since the remaining task is just computing scattering amplitudes, let me just show you the results. So this is the results, and there are many diagrams, but the diagram which gives the leading contribution are shown here, and this piece is the contribution from the diagrams which doesn't contain the graviton,
You have
which are
5 more
shown to be
minutes.
positive. Okay. And the second piece is a diagram which includes a T-channel exchange of graviton. And interestingly, the gravitational piece, C-grav, is negative, while the C non-grav is positive. So the positivity bounds implies that some positive quantity plus negative quantity must be larger than some quantity. So this can be non-trivial. And in particular, this inequality is non-trivial when the negative C-grav dominates over the sign indefinite term, over the right-hand side. In this case, we can forget about this ambiguity, and we can discuss this inequality, implication of an inequality. And in particular, if we consider this limit, so if we fix the dimensionless coupling lambda and G over M, and take the massless limit, then this piece becomes minus infinity. So then it is definitely, it leads to the violation of inequality. So this indicates that the potential cannot be arbitrarily flat. And to make the implication of this inequality clearer, so let us consider when having a scaling of this form. And then the inequality can be rewritten in this simpler form, which basically gives a lower bound of the mass. But in general, the inequality contains the mass and coupling constant and the cutoff scale. And in particular, in lambda 5 theory, this bound becomes simply a lower bound of the mass. And the lower bound is plotted here. So here the shaded region is the excluded region, and this blue dotted line expresses that the negative gravitational part equals to the ambiguous right-hand side term. And below this line, the gravitational piece dominates over the ambiguous term, so the bound is reliable. And this red line shows that the bound is saturated. And to draw this figure, we use this value, but we can plot this kind of figure for given coupling parameters. And I just show you this figure, and just for example. And our bounds provides quantitative Swampland criteria. And let us make some comments on the results. So firstly, it is found that the bounds are consistent with important models, such as axion-like particle models of this form, or the Starobinsky inflation model. So in this sense, the implication is not so interesting, but the application to the Higgs boson can be interesting, because if we naively apply our results to the Higgs potential, then we can argue that we obtain the cutoff around the 10 to 10 GeV. But of course, in reality, we have also other particles, including W boson and so on. So we should perform the full analysis in standard model, and that's in progress. And finally, it will be interesting to compare our results with related Swampland conjecture, the strong scalar gravity conjecture, which is given in this form, which basically states that the scalar force should be stronger than the gravitational force. And this bound provides a non-trivial bounds for very tiny couplings. And for example, if we apply this bound to axion-like particles, then we obtain the upper bound on the decay constant. On the other hand, our bound constrains the potential for larger couplings, because for tiny couplings, the negative gravitational terms is beaten by the ambiguous term, so our bounds cannot be reliable. So this means that our bound is complementary to the strong scalar gravity conjecture, but it's more precise and the underlying assumptions are clear. So this is the summary and prospects. And okay, so we derive some gravitational positivity bounds in clear assumptions, and then we apply this bounds. Sorry, so it's time. So we derive Swampland conditions on scalar potentials and the clear assumptions. And we find that the scalar potentials cannot be arbitrarily flat, and there are various prospects, various directions. Yes, thank you very much.
Thank you very much. So let's thank Junsei. And are there any questions? If so, please raise your hand and I will call you. Gary, go ahead.
Hi, very nice talk. I was wondering, other than 2-to-2 scattering with light external states, have you considered conditions from scattering of the higher spin external states and see if you can sharpen the bound?
Yes, external states.
So this is only 2-to-2 scattering. There could be additional conditions coming from other scattering. In particular, the external states don't have to be photons.
N to N.
Yeah. Or
you're talking about N to N?
That's one possibility, N to N. Or the external states may not be the like degrees of freedom. It could be some of the highest
heavy states.
Yeah.
Yeah, that's possible direction. Yeah. Yeah, I didn't do that, but
thank you.
Sorry.
Okay, then Jose.
Hi, thanks for the very nice talk. So you say that your bound means that the potential cannot be arbitrarily flat. But how is that compatible with models with extended supersymmetry, which actually the potential is just zero, is totally flat?
Exact shifted symmetric potential. Okay. So in that case, I didn't explain that, but actually that potential is allowed because in that case so you're talking about the exactly flat potential, correct? Yes. In that case, so this gravitational piece also, so all terms vanishes in that case. So there's no non-trivial bounds in that.
So as long as you have G different from zero is when it applies the bound. If G is zero, it vanishes. Okay, I see. Thanks.
Yeah, sure.